Today we will explore why mapping the Higgs potential at a new, more powerful particle collider could be one of the most important undertakings in modern physics.
It is a strange fate that we should suffer so much fear and doubt over so small a thing. Such a little thing.
Charting the evolution of the Higgs quantum field since the dawn of our universe is one of the most important pillars of the physics programs planned for new, more powerful particle colliders. Today, we ask a simple question. Why is mapping the Higgs potential and obtaining a better understanding of exactly how fundamental particles acquired their mass of such paramount importance? Many reasons. However, before we can answer that crucial question, a quick review of episode 3, the Higgs potential and electroweak symmetry breaking. Review episode 3 for a more thorough breakdown. According to quantum field theory, the vacuum of our universe is not really empty, but rather a boiling sea of quantum fields associated with every fundamental particle we know and do not yet know. One of those quantum fields is the Higgs field. All of these fields have an associated potential, which depends on the strength of the field in the vacuum. Usually the potential energy distribution of quantum fields takes a parabolic shape, and these fields, although oscillating, take an average value of 0. The value of the field that minimises the potential energy. Systems like to sit at energy minima. We can excite fundamental particles out of the fields by pumping energy into them, like we do at particle colliders, but on average, these fields are turned off. The Higgs potential is the Higgs field's vacuum energy density, the energy density stored in the omnipresent Higgs field, the Higgs field's contribution to the energy density of empty space. The Higgs potential is dependent on the strength of the Higgs field in the vacuum of our universe. According to the standard model, a 4-component Higgs field existed in the very earliest moments of the universe. At this point, the universe was incredibly hot and dense, and the Higgs potential took a typical parabolic form. The vacuum of our universe sat at the minimum of the potential, the origin, and all the components of the Higgs field took an average value of 0. Fundamental particles therefore were massless, and whizzed around the early universe at the speed of light. However, after around 10 to the minus 11 seconds, as the universe expanded and cooled, its temperature dropped below a critical temperature, and the shape of the Higgs potential morphed from parabolic into the wine bottle or Mexican hat-shaped classical standard model Higgs potential, typically presented in particle physics outreach materials. The Higgs potential developed a ring of new, lower energy ground states, and the vacuum of our universe naturally rolled from the origin down the potential hill and into one of those lower energy ground states, much like a ball rolling down a smooth hill. This process imbued the weak bosons, the W+, W- and Z, with mass, a phenomenon known as electroweak symmetry breaking, and also powered up the scalar Higgs field. This produced a constantly switched on quantum treacle everywhere in our universe. Fundamental fermions began to ping off this field and also acquired their mass. As such, the changing form of the Higgs potential solves a number of deep problems in particle physics and provides the simplest and crudest explanation for how fundamental particles, excluding neutrinos, acquire their mass. However, there is a massive, gaping hole in our picture of how fundamental particles acquire their mass. Despite the importance of the Higgs potential in explaining the evolution and current state of our universe, and despite the ubiquity of the infamous classical standard model Higgs Mexican hat potential in popular physics media, the true shape of the Higgs potential has never been experimentally validated. The form of the Higgs potential in the standard model is the simplest and crudest that gets the job done. The bare bones form of the potential that ensures that the weak bosons and fundamental fermions are massive in our modern universe. However, there are many different ways to roll down a potential hill and produce a universe full of massive particles. As such, there are many competing theoretical shapes of the Higgs potential. Just as particle physicists assumed the Higgs boson existed for the more than 50-year span between Higgs's seminal papers and its discovery at the Large Hadron Collider in 2012, physicists are still assuming that our standard model picture of electroweak symmetry breaking is correct and complete. But what if it isn't? It's very possible that our standard model picture of electroweak symmetry breaking and the evolution of the Higgs potential is wrong. This realization leads us to the focus of this episode, and a burning question. Why should we care? The standard model Higgs potential gets the job done, and takes the simplest and crudest form required to explain the universe of massive particles we live in. Aren't we done here? Why should we care about the true shape of the Higgs potential? Why should we care how our universal vacuum has evolved? Why should we care about the nature of electroweak symmetry breaking? And in the end, why should we care enough to build larger, more powerful and more expensive particle colliders to study these matters? Well, I'm very glad that you asked, because understanding the shape and evolution of the Higgs potential and the true nature of electroweak symmetry breaking could be one of the most important undertakings in modern physics. The first reason we want to map the true Higgs potential of our universe is to check whether the standard model classical Higgs potential really is the Higgs potential of our universe. The discovery of the Higgs boson in 2012 at the Large Hadron Collider told us that the Higgs field exists. Subsequent experimental interrogation of the Higgs boson tells us that the mass of the Higgs boson is related to the masses of the weak W and Z bosons, just as the standard model predicts, and that the Higgs boson couples to fundamental particles with strengths in proportion to their masses, again in line with standard model predictions. However, these studies have revealed surprisingly little about the form of the Higgs potential. We have very little idea whether the form outlined by Peter Higgs in the 1960s is accurate. We have very little knowledge of how the vacuum of our universe came to rest at its current position. As such, physicists' model of how fundamental particles acquired their mass is sufficient, but very far from complete. We need to experimentally verify the shape of the Higgs potential and validate or refute the standard model. Despite the anti-nuclider position staked out by some of our most well-known physics influencers, and despite their constant downplaying of the critical importance of Higgs physics, even they realise that it's not appropriate for physicists to assume that the Higgs sector behaves exactly as the standard model contends. Indeed, any deviations in the true Higgs potential of our universe from that predicted by the standard model would be completely revolutionary, and an instant indication of the presence of beyond standard model physics in the Higgs sector. The Higgs boson is an incredibly unique new probe of our universe. It is the first ever seemingly fundamental, spin-free scalar particle that we have ever observed, and the only one that exists within the framework of the standard model. What's more, as we saw in episode 2, 15 of the 19 free parameters in the standard model are directly linked to the Higgs sector. So if we ever want to understand why the standard model takes the form it does, we have to interrogate the Higgs. Discovering this black swan, and then simply asking the science community and the public to assume that it behaves exactly as theoretical predictions suggest is, to my mind, a bizarre position to take. Given the Higgs's unique nature and its paramount importance and centrality to the standard model, we must check every aspect of its behaviour and track down any discrepancies from the behaviour outlined by the standard model. Indeed, many beyond standard model hypotheses predict specific patterns of deviations in the Higgs potential of our universe. So by probing the Higgs potential very precisely, alongside making other precision measurements in the Higgs sector, we may be able to tease out the nature of beyond standard model physics and where new particles, forces, and physics are hiding. However, that's just the nuts and bolts procedural part. We aren't just looking to validate or refute the standard model, as certain influencers would have you believe. We have far grander plans. We want to go much, much further and understand the true nature of electroweak symmetry breaking, exactly how it happened, exactly why it happened, and the additional physics it may hide. As physicist Frank Close points out, finding the Higgs boson was only the start of our quest to understanding the electroweak phase transition of our universe. The more ambitious goal is to identify and understand the nature of electroweak symmetry breaking, the asymmetry that is key to the material universe. The Higgs boson is but its herald. Discovering the Higgs boson was only our first step towards unravelling the mystery of how and why fundamental particles acquire mass. One key question we want to ask is whether one single Higgs field did all the work in electroweak symmetry breaking. Is one single Higgs field responsible for giving fundamental particles their mass? As we have seen, the standard model Higgs mechanism, dependent on the standard model Higgs field and Higgs potential, is the simplest and crudest model that gets the job done. It is a model that can explain why the weak gauge bosons are massive, and why the scalar Higgs field is constantly powered up throughout our universe, allowing fundamental fermions to ping off it and acquire mass. However, that does not mean that it is the complete picture of electroweak symmetry breaking. Higgs and his contemporaries postulated the existence of a single 4-component Higgs field in the very early universe, a field that had just the right properties and provided just the right amount of spontaneous symmetry breaking to produce a universe full of massive fundamental particles. However, it's perfectly reasonable to ask whether there are additional scalar fields or more Higgs fields that contributed to the process of electroweak symmetry breaking. We have found one Higgs boson, the excitation of one scalar Higgs field. But could there be more just waiting to be found? If the history of particle physics has taught us anything, it's that the universe regularly fails to implement the most minimal solution to a problem. A simple example being the fact that the standard model contains 3 generations of fundamental fermions, 3 very similar families of fundamental particles. Why? To channel Isidore Rabi, who ordered those? Why should electroweak symmetry breaking be any different? Why should it be completely solved by our first theoretical model, one singular Higgs field, and Peter Higgs's 3-page paper? Given the discovery of the Higgs boson, we know that at least one fundamental scalar quantum field exists. The smart money might suggest that there are more. In the 20th century, we discovered the low mass quarks first and the higher mass quarks later, as colliders increased in energy. Perhaps a bountiful scalar sector lies just above our current energy reach, or perhaps more Higgs bosons are hiding in the noise produced by a messy hadron collider, like the Large Hadron Collider. Perhaps we stand on the brink of a scalar revolution. Many beyond standard model hypotheses include extended Higgs sectors and posit the existence of additional scalar fields in the universe and additional related Higgs bosons. Theoretical models with extended Higgs sectors are incredibly attractive, as they also address several unresolved problems in particle physics. Theoretical calculations showed that an additional Higgs boson could produce a stable dark matter candidate that is in compliance with all current experimental constraints from dark matter search experiments, and could produce the abundance of hypothetical dark matter we observe in the universe today. Extended Higgs sectors can also radically change the shape of the Higgs potential, and potentially explain the dominance of matter over antimatter we observe in the universe, something we will return to shortly. Many of these beyond standard model hypotheses predict specific patterns of deviations in the Higgs potential of our universe, or other Higgs boson properties, relative to those predicted by the standard model. So by probing the Higgs potential very precisely, alongside making other precision measurements in the Higgs sector, we may be able to infer the existence and nature of aspects of beyond standard model physics, and potentially search for related forces and particles directly at new high-energy colliders. Given that extended Higgs sectors can address so many open questions in particle physics simultaneously, it is essential that we study the Higgs boson and its potential in detail, and confirm or constrain the presence of such extended sectors. So we want to understand exactly how electroweak symmetry breaking occurred. But there's also another massive question we want to answer. Why did electroweak symmetry breaking occur? Electroweak symmetry breaking was driven by a morphing in the shape of the Higgs potential, According to the Standard Model, the shape of the Higgs potential is described by an incredibly simple formula. At high temperatures in the very early universe, the mu squared or mass squared term and the lambda or self-coupling term were positive, and the Higgs potential took a parabolic form typical of quantum fields. However, as the universe expanded and cooled, the temperature fell below a critical temperature. The mass squared term flipped negative, the Higgs potential developed a ring of new lower energy ground states, and the vacuum of our universe rolled down the Higgs potential hill, imbuing mass to the weak gauge bosons and powering up the Higgs field throughout our universe. Fundamental fermions could then ping off this field to obtain their mass. The Standard Model form of the Higgs potential, outlined by Peter Higgs, can describe this process. It can give you how the process happened, but it doesn't explain why it happened. Why did the mass squared term of the Higgs potential flip from positive to negative as the universe expanded and cooled? Why, as my colleague Patrick Mead points out, do we owe the mass of fundamental particles, and hence our very existence, to a minus sign? Phase transitions like this in a system are usually dependent on underlying microscopic dynamics. When type 1 or BCS superconductors are cooled below a transition temperature, electrons inside the superconductor form Cooper pairs and facilitate the phase transition to a superconducting phase. As our early universe expanded and cooled, the hot dense quark-gluon plasma underwent a QCD phase transition to form the heavy hadronic matter, protons and neutrons, that we see today. When a ferromagnet cools below a transition temperature, its magnetic dipoles go from thermally wobbling in all directions to all being able to point in a similar direction. This new ability to align up or down creates new, lower states of energy, states that the system naturally rolls into. For a full breakdown of this process, check out section 2 in episode 3. All of these transitions can be explained by underlying microscopic dynamics and by an underlying Mexican hat-shaped potential. Indeed, in episode 3, we saw that the Mexican hat form of the Higgs potential was copied and pasted from Lev Landau's work on phase transitions in ferromagnets. This leads us to an amazing realization. Whenever we see a phase transition of a system that can be described by the Mexican hat potential, the reason that phase transition occurs can often be understood in terms of underlying microscopic dynamics. Electrons pairing up, quarks and antiquarks forming a condensate, or magnetic moments locking into place. But if that's the case, what are the underlying microscopic dynamics that explain the electroweak phase transition and the evolving form of the Higgs potential? We currently have no idea. Are there similar microscopic dynamics which explain why the electroweak phase transition occurred in our very early universe? Physicists are desperately seeking the answer to this deep mystery and have some revolutionary ideas that can be tested at a new, more powerful collider. Many theorists believe that underlying microscopic dynamics do explain the electroweak phase transition, and that the Higgs boson itself must be a composite particle, made of even more fundamental constituents. This is a very alluring proposition. The Higgs boson is the only fundamental spin-free scalar particle in the Standard Model. It seems to be completely on its own within the framework, a black sheep amongst fundamental particles. But perhaps it isn't unique at all. Perhaps it is made up of more fundamental particles with spin, and is only spin-free overall. Perhaps the Higgs boson is a scalar particle, like the pion made of a quark and antiquark is a scalar particle. Think about it. Every time we have smashed particles together with higher energy, we have revealed a new layer of nature. Smashing lumps of material revealed atoms. Smashing atoms revealed protons, neutrons and electrons. Smashing protons and neutrons revealed quarks. It would be very curious if we'd reached the Russian doll at the centre of nature only several decades after turning on the very first particle colliders, and given the plentiful orders of magnitude in energy between the collisions at the Large Hadron Collider and the Planck scale. Composite Higgs models can also alleviate the so-called electroweak hierarchy problem, a problem we'll wrestle with later in this series. For now, realise that according to our current understanding, if the Higgs is a fundamental scalar particle, it should not, according to our current understanding of quantum field theory, be able to display the low mass that it does. Of course, if the Higgs is not a fundamental particle, that problem completely evaporates. But how can we determine if the Higgs is composite at a new, more powerful collider? Well, consider the analogy of an atom. At large distances, an atom looks like a neutral object. However, when we zoom in to shorter distances, we notice that it contains positive protons and negative electrons. It's only neutral overall. The motion of these negative electrons can produce weak, fleeting, second-order van der Waals interactions with other atoms, interactions that shouldn't exist if the atom truly were a neutral blob. As such, the composite nature of the atom is encoded in its behaviour and interactions with other particles. In a similar fashion, if the Higgs boson is composite, that composite nature should be encoded in deviations of the Higgs boson's couplings to other particles, and also to other Higgs bosons, relative to those predicted by the Standard Model. The shape of the Higgs potential is in turn dependent on the interaction strength between multiple Higgs bosons. So, if we can map the Higgs potential and take other exquisite measurements of the Higgs boson, such as its coupling to other Standard Model particles, at larger, more powerful particle colliders, we may be able to infer the presence of a new layer of nature beneath the Higgs. In addition, if the Higgs is made of more fundamental fermions, those particles should also interact in different ways to create a tower of bound states, and not just the Higgs boson. Consider the proton and the delta plus baryon. Both consist of 2 up quarks and 1 down quark, yet the delta plus has a significantly higher mass and is treated as a completely separate particle to the proton. Why? The difference is caused by exactly how the particles and their spins interact with one another inside these composite particles. If the Higgs is composite, we may be able to produce and capture excited states of the components of the Higgs at new colliders. We may be able to produce and capture new bound states, new particles. Of course, if a new layer of nature refuses to appear, and the Higgs truly does seem to be fundamental, we still need to seek to explain why electroweak symmetry breaking occurred. It is extremely difficult to prove definitively whether a particle is fundamental. After all, maybe we just need to hit it harder to break it apart or reveal its composite nature. However, using a particle collider, we can set an energy scale up to which the particle behaves as if it were fundamental. We can set bounds. Theorists also have a whole suite of ideas to explain electroweak symmetry breaking, even if the Higgs is fundamental, and many of these can be tested at a new collider. Radiative electroweak symmetry breaking, neutral naturalness, cosmic selection, and many other models. A new, more powerful particle collider is a Swiss Army knife for testing new particle physics theories. One of these theories is radiative electroweak symmetry breaking. Without getting into the specifics of the theory, this approach received significant coverage around a decade ago, as it can predict the form of the Higgs potential and, under certain constraints, almost the exact 125 GeV mass of the Higgs boson, all from first principles. This is something the Standard Model simply cannot do. The upshot of this section is that by carefully mapping the Higgs potential at larger, more powerful particle colliders, we may also be able to understand the nature of electroweak symmetry breaking, even if the Higgs is truly fundamental. What we need to realise is that spontaneous symmetry breaking occurs in many systems. However, spontaneous symmetry breaking can occur in a range of different ways, and as a result of incredibly different physics and incredibly different underlying microscopic dynamics. We understand the origins of such symmetry breaking in ferromagnets or type 1 superconductors. However, after more than 60 to 70 years, we still do not understand the origin of spontaneous symmetry breaking and the transition to the superconducting phase in type 2 superconductors, the type that make the superconducting magnets of the Large Hadron Collider viable. Is this transition facilitated by long-range multi-particle interactions, super exchange, vortices? After decades of study, we still do not yet understand why symmetry breaking occurs in the materials we use inside our most powerful particle colliders and most high-tech medical scanning devices. Understanding this conundrum could be the key to manufacturing such vital materials more efficiently, more cheaply, and even for room temperature applications central to tackling climate change. After decades of study, we are still unclear as to why type 2 superconductors work. failing to build new colliders and essentially pulling the plug on understanding how electroweak symmetry breaking works after a comparatively minuscule amount of time is, to my mind, an incredibly strange path for fundamental physics to walk. Explaining why electroweak symmetry breaking occurred in the early universe is outside the realm of the Higgs boson. And yet at the same time, by studying the Higgs boson at new colliders, we may finally understand its origin and why we are here in the first place. Another key matter we want to address at new colliders is how the Higgs potential has changed as the universe has evolved. We want to map the electroweak phase diagram of our universe. This may be the key to understanding how the very matter that created us came to be, and how the universe as we know it will end. According to the standard model, the Higgs potential took a parabolic form in the hot, dense, early universe, before unfurling into its current Mexican hat form as the universe expanded and cooled. That's a pretty picture, but how can we confirm that that's what really happened? We don't currently live in the hot dense plasma that existed nanoseconds after the Big Bang. To understand how the shape of the Higgs potential changes with temperature and the cooling of our universe, we need to understand the current shape of the Higgs potential extremely precisely. Then theorists can perform what is known as thermal quantum field theory. They can calculate how the Higgs potential of our universe would look if the temperature of the universe were raised, if we went back in time. Taking these calculations and well-established models of how the temperature of the universe has changed during its expansion, theorists can confidently predict how the Higgs potential must have looked at various stages in the past, and they can then give us the electroweak phase diagram of our universe. They can then test the picture of the electroweak phase transition predicted by the standard model. We want to understand how the form of the Higgs potential changes with temperature, and whether those changes track with those predicted by the standard model. Does the standard model continue to hold as we dial up the temperature of our universe? Using new colliders, we want to understand whether the standard model, our most successful and accurate description of the universe at its shortest scales, holds up when the vacuum of our universe was in two different phases, one before and one after the electroweak phase transition. Essentially, this is the same as mapping the phase diagram of a substance like water. In that case, we want to know how the substance looks and behaves as we change the temperature and pressure and observe its different physical phases: solid ice, liquid water, and gaseous steam. We also want to check whether our underlying model of atomic interactions can describe water in these different phases: solid, liquid, and gas. Imagine if our understanding of atomic interactions could only explain the behaviour of ice, but not water. We know that the standard model explains the current watery phase of our universe very well. But what about the previous ice phase of our universe before the electroweak phase transition? Will it still hold? We currently have no idea. We need to ask important questions, like whether the electroweak symmetry really is restored at extremely high temperatures, as the standard model predicts. If we heat up the universe, do we go back to a state where all particles are massless? Theoretical physicists such as Steven Weinberg went against the standard model prediction and contended that the electroweak symmetry may never be restored. Again, currently, we simply do not know. Despite the familiarity of the Higgs Mexican hat, in reality, we have no clue if or how the vacuum of our universe rolled down the potential hill to its current stable vacuum position. We want to find out. To do so, we need to build larger, more powerful, and more expensive particle colliders. Okay, so that's all very interesting, but again, cards on the table. Who cares? Why should you care about how the vacuum of our universe arrived at its current state, and the evolution of an esoteric potential billions of years before the Earth even existed? I'll tell you why. Because it may explain why the very matter that makes up our bodies even exists. Quantum field theory dictates that every fundamental particle must have a corresponding antiparticle, a partner with exactly the same mass but an opposite electrical charge. For every electron, there is an anti-electron or positron. For every quark, there is a corresponding antiquark. However, you might have noticed that we don't see very much of this antimatter in the universe around us. All the electrons we encounter are negative. All the protons we encounter, composed of quarks, are positive. Where is all the antimatter? This discrepancy is known as the matter-antimatter asymmetry and has been a persistent puzzle in particle physics for decades. Indeed, it was the focus of my own PhD. Our best models of the early universe insist that equal amounts of matter and antimatter were created in the Big Bang. However, in the very earliest nanoseconds of the universe, a minor excess of matter over antimatter developed. The matter and antimatter then collided and annihilated to form photons. This created the universe we see today, a universe awash with photons and a small amount of leftover matter that went on to create the stars, the planets, and us. But how could such an imbalance have developed in the very earliest nanoseconds of our universe? It turns out that the true form of the Higgs potential in our universe may provide the solution. According to the standard model, when the electroweak symmetry was broken, the vacuum of our universe rolled down the Higgs potential hill from an unstable point towards the energy minima at the bottom of the hill, our current vacuum. In general, there are two possible ways that such a symmetry breaking process can occur. 1. The potential hill can be smooth and continuous, without any false minima in which the system can get stuck. We call such transitions second-order phase transitions. Or 2. The potential hill can have at least one false minimum along its path where the rolling system can get trapped. This is on top of the valley at the very bottom of the hill. These transitions are known as first-order phase transitions. In the case of a second-order phase transition where the potential hill is smooth and continuous, the symmetry breaking proceeds smoothly as well. Every part of the universe switches on the Higgs field at the same rate. The vacuum maintains one homogeneous but changing vacuum. The vacuum is the same everywhere within the universe throughout the transition to the current minimum. This phase transition is akin to ice melting slowly and smoothly in a warm room. This is how the electroweak phase transition occurred according to the standard model. The standard model classical Higgs potential is smooth, and there were no opportunities for the vacuum of our universe to get caught in a false vacuum minimum state. Instead, the vacuum of our universe transitioned continuously from its high energy phase in the very early universe with the Higgs field powered off, down to the low energy state with the Higgs field powered on of the modern universe. However, given that we do not know the shape of the true Higgs potential, it's possible that the true Higgs potential of our universe is not smooth, and instead contains a false minimum in which the vacuum of our universe could have become trapped on its way to its current state. If that were the case, as the electroweak phase transition proceeded in the early universe, parts of the universal vacuum would have been trapped in the early high temperature phase, while other parts quantum mechanically tunneled to our current lower energy, low temperature phase. Bubbles of the new low energy vacuum would have developed and expanded as the electroweak symmetry broke discontinuously and in pockets, like bubbles of steam developing at different locations as a pan of water is heated. In this first order phase transition, the universe would have been severely out of thermal equilibrium and literally boiling as the electroweak phase transition took place. Again, that's all very interesting, but how does it relate to the matter-antimatter asymmetry we observe in our universe? Well, in 1967, physicist Andrei Sakharov proposed 3 necessary conditions that an interaction must specify to produce matter and antimatter at different rates. These conditions were inspired by the recent discoveries of the cosmic microwave background and so-called CP violation in the neutral kaon system. The 3 necessary Sakharov conditions are: 1. Baryon number violation. Simply put, a process needs to be capable of generating more quarks and antiquarks if we want to produce the matter-dominated universe that we see today. 2. C symmetry and CP symmetry violation. Any process must treat particles and antiparticles differently. For example, a particle and its antiparticle must decay at different rates. And 3. A process must occur in conditions that are out of thermal equilibrium. If thermal equilibrium exists, any developing excess of matter over antimatter will be corrected by processes producing more antimatter than matter. If a process allows these 3 conditions to coincide, it's possible to generate a matter-antimatter asymmetry Even if we start from equal amounts of matter and antimatter, the conditions we assume prevailed after the Big Bang. If we assume that the standard model still explains physics well in the very early universe, the C violation and CP violation observed in weak decays, and the second order electroweak phase transition predicted by the standard model, produce only a negligible matter-antimatter mismatch in the first nanoseconds of the universe. This mismatch is 10 billion times too small to explain the matter-dominated universe we observe today. However, things change very significantly if the true Higgs potential of our universe is discontinuous and facilitates a first-order electroweak phase transition. One process that could have created such a matter-antimatter asymmetry is known as electroweak baryogenesis. As we have seen, a first-order electroweak phase transition could have created extreme outer-thermal equilibrium conditions, ticking one of the Sakharov conditions. The standard model itself can tick the other two. The standard model facilitates C violation and CP violation, and can also facilitate baryon number or B violation through a mechanism known as the Sphaleron process. Without getting into needless details, the Sphaleron process violates both baryon number and lepton number conservation, but conserves the combination of baryon number minus lepton number. It can therefore generate more quarks than antiquarks. It can create a matter-antimatter asymmetry. This Sphaleron process is particularly active at high temperatures, but almost completely turned off at lower energies and temperatures. This means that in the very early hot dense stages of the universe, before the electroweak phase transition, the Sphaleron process could have created a significant excess of quarks over antiquarks. However, we need a way to lock in those excesses going forwards, and not to just have them arise and then dissipate. We need a way to keep them in our universe. That's where the first order electroweak phase transition comes in. If we had a first order electroweak phase transition, as pockets of the universe tunneled from the high temperature phase to our current vacuum state, bubbles of the modern vacuum would have begun to nucleate and grow. As these bubbles expanded, they rapidly converted more of the vacuum of our universe to the current, cold, low energy vacuum state. And when they did so, they instantly switched off the high energy Sphaleron processes occurring in the high temperature phase continuum. When this happened, they instantly locked in the excesses of matter over antimatter that these Sphaleron processes had produced. They safeguarded the minimal dominance of matter over antimatter that would eventually ensure our existence. These bubbles and these collisions of phases could even have produced low energy gravitational waves that may be detectable by future space-based gravitational wave observatories, such as LISA. The upshot is that if we can map the Higgs potential at new colliders and determine that it has a first-order phase transition, we may be able to begin to explain why any of us are even here, and all with minimal tweaking of the standard model. That sounds like a pretty good trade-off to me. It turns out that given the mass of the standard model Higgs boson of 125 GeV, the only way we know of to get a first-order electroweak phase transition is for additional scalar and/or Higgs fields to exist in the very early universe. The existence of a first-order electroweak phase transition and potentially additional scalars or even additional Higgs bosons associated with these additional fields could be readily sought at new, higher energy colliders. Understanding the order of the electroweak phase transition would give us an insight into the very earliest evolution of our universe, insight that perhaps only the particle physicist, unobscured by the cosmic microwave background, can provide. Of course, we're not only interested in the very early evolution of our universe, we also want to know where the universe is headed, where this train will stop. And it turns out that understanding the Higgs potential may be the key to identifying that destination. The Higgs potential may control how the universe, as we know it, will end. The vacuum of our universe is a writhing maelstrom of fundamental quantum fields, associated with every fundamental particle we know and do not yet know. These fields fluctuate, and these fluctuations have an associated energy density. As we have seen, the classical standard model Higgs potential is ripped straight from Landau theory, and not calculated from scratch in quantum field theory, the language underlying the rest of the standard model. If we want to calculate the Higgs potential of our universe in quantum field theory, the calculation depends on how the energy density of empty space varies with the strength of the Higgs field. We know this. But also, and crucially, on the energy of the fluctuations of any other fundamental field that the Higgs sector interacts with. Energy from the fluctuations of the top quark field, the W boson field, the Z boson field, the bottom quark field, the tau lepton field, and so on. Think of it this way. The Higgs gives mass to all other particles, but all other particles give mass to the Higgs through quantum corrections to the mass squared term of the scalar field. Since these fields contribute to the mass squared term in the Higgs potential, they add quantum corrections to, and alter the shape of, the Higgs potential. These schematic plots demonstrate the contributions to the Higgs potential, the energy density of empty space, from these standard model fundamental fields, and how they vary as the Higgs field strength changes from 0 to a maximum value, Vmax. These standard model contributions to the Higgs potential can be calculated, at least approximately, for any Higgs field value from 0 up to that cutoff, Vmax, and for all quantum fluctuations with an energy less than roughly Vmax again. The cutoff, Vmax, represents the boundary up to which we can confidently apply the standard model alone. It's as far as we can push up the Higgs field strength and still believe our calculations within the standard model. Above Vmax, contributions from beyond standard model physics, whatever form they may take, must be included in our calculations, and given that we don't understand the nature of beyond standard model physics, this becomes difficult. However, there's another problem. No one knows what the cutoff, Vmax, is. Given that we haven't seen any signs of beyond standard model physics at the LHC, Vmax appears to be greater than about 1 TeV or so. However, if there really is an energy desert between the electroweak scale and the Planck scale, Vmax could be as much as 10 to the 15 times larger than that. Let's assume that the energy scale of any new beyond standard model physics is high above the electroweak scale of about 1 TeV, probed at the LHC, i.e. our cutoff Vmax is far higher than 1 TeV. We can then calculate the standard model quantum field theory contributions to the Higgs potential, where h is the strength of the Higgs field, Vmax is the scale of any new unknown physics that interacts with the Higgs, and the m terms represent the masses of various particles that interact with the Higgs. Now let's assume that there is no new physics beyond the standard model until we reach roughly the Planck scale at around 10 to the 16 TeV, and quantum gravity effects become important. Under that assumption, we can enter the Planck scale as the scale of new physics, our Vmax, and continue to ignore the contribution of new physics up to incredibly high Higgs field strengths. Essentially, we're assuming that the standard model holds all the way up to the Planck scale, where gravitational effects must become important. This theoretical quantum Higgs potential is equal to the classical potential, posited by Higgs and his peers, in the region around our current vacuum expectation value. As the Higgs field is cranked up, away from the current expectation value of our universe, the Higgs potential calculated by quantum field theory begins to rise, just like the classical standard model Higgs potential, ripped straight from Landau theory, starts to rise. However, as the Higgs field strength continues to grow, the dominant negative top quark mass term forces the quantum theoretical Higgs potential to turn over and begin to fall. It starts diverging from the classical standard model Higgs potential. As such, according to quantum field theory calculations, it's possible that the Higgs potential of our universe could fall to an energy density minimum below that of our current vacuum, if the Higgs field strength were much higher. This higher Higgs field strength will produce a lower energy, more stable vacuum than that of our current universe. This means that our current vacuum may only be metastable, a stop-off point on the way to the true vacuum ground state of our universe. If that's the case, the vacuum of our universe may be able to quantum tunnel into that new minimum. If that were to happen, the results would be catastrophic. The values of particle masses would instantly change, and the physics that governs our universe would be fundamentally altered. A bubble of vacuum governed by entirely new Higgs physics would propagate through the universe, and we would be obliterated. The most recent standard model calculations indicate that this metastable scenario might apply to our universe, and that when the Higgs field reaches a field strength of about 10 to the 11 GeV, the Higgs potential becomes negative and develops a new, true global vacuum minimum at a Higgs field strength of about 10 to the 17 GeV. However, don't despair and fear vacuum collapse. The height of the barrier between our current vacuum and this hypothetical lower energy vacuum is as high as 10 to the 39 GeV to the 4, and the probability of our vacuum tunneling to that lower energy state is vanishingly small. A direct calculation within the framework of the Standard Model suggests that the likely lifetime of our vacuum state is greater than 10 to the 58 years. That's pretty long. And other studies suggest that particle colliders and cosmic rays have a completely negligible chance of catalyzing and causing such a tunneling event. Particle colliders are unlikely to kill us all, despite what some people might tell you. It should also be noted at this stage that the stability calculations we have just discussed are very sensitive to uncertainties in the values of the top quark mass and the Higgs mass. While our vacuum appears to sit in the region of metastability, it is within 2 sigma from the stability region, and this result may change with improved calculations of the Higgs and top quark masses at new colliders. In addition, the assumption that the Standard Model holds all the way up to the Planck scale is an assumption that the vast majority of particle physicists believe to be very suspect, and would wreak havoc in other areas of physics. After all, we know the Standard Model must break at some point, as it currently has no explanation for dark matter, dark energy, the masses of neutrinos, and several other phenomena. Indeed, if Vmax were pushed all the way to the Planck scale as we've assumed, the huge strength of the Higgs field would make top quarks so heavy that they'd collapse into tiny black holes. So there's no need to don the sandwich boards and start praying just yet. We won't be flashing out of existence anytime soon. At least, probably not. However, it is incredibly intriguing that given everything that we know, our universe appears to be teetering on the brink of stability. That doesn't seem natural. More on those ideas in episode 5. What we should take away from the discussion of the last 2 sections is not that we have a perfect understanding of the evolution of the early universe, or how the universe may end, but rather that the Higgs potential is central to getting a handle on both. And as such, building new colliders is central to getting a handle on both. In this episode, I have introduced you to some of the main reasons why mapping the Higgs potential is so vitally important. There are many more reasons. For example, depending on the shape of the Higgs potential, the Higgs could also have a bearing on other huge universal problems. Some models even predict that the Higgs field is responsible for cosmic inflation, a period of extremely rapid expansion of the universe which occurred for a fraction of a second after the Big Bang. However, without diverting into those additional discussions, the takeaway message of this episode is that mapping the Higgs potential is so incredibly important because it allows us to wrestle with some of the most consequential, deep, and long-standing questions. Such an undertaking allows us to seek to understand where we are, where we come from, why we are here, and where we are heading. These are some of the most fundamental questions, and these are questions that only particle physicists can address. Now that we understand why mapping the Higgs potential is so important, in episode 5 we will discuss how the Higgs potential can be mapped, and why such mapping relies on the funding, building, and running of new, more powerful particle colliders. See you next time. I want to know what you think, because you're the scholars of enlightenment that I do this for. So please take a moment, if you wish, to let me know down in the comment section. And if you like this video, please consider leaving a like, subscribing, setting up notifications, and sharing this video more widely. I can't tell you how much these simple actions help me out and how much I'd appreciate it. Thanks for watching. Thanks for being scientific. Thanks for being bad.